del square H plus omega square mu epsilon H is equal to 0. These are what we have. These are named after the scientist Helmholtz. These are called Helmholtz equations. And we have seen a specific solution.
Note down this important.
We have seen a specific solution for that, which was the plane wave. We have assumed that the electric field was pointing in x direction but varying in z, and we had said that this was an A E minus jkz pointing in x direction. And at that same time, we had seen that if this electric field exists, then Maxwell's equations dictate that there should be a component of H field, a magnetic field in y direction, and its magnitude is given by A E minus jkz divided by eta, but is pointing in y. We have noticed that if I look at E cross H, the direction of E cross H, that gives me the direction of wave. And the various terms we had, which we have introduced now, is the angular frequency omega, which was 2 pi f, k, which was 2 pi by lambda, which is the wave number, v, phase velocity, which was omega square root of mu epsilon, and wave impedance eta, which is basically how E and H are related by each other. What is the magnitude of E divided by H? And that was square root of mu epsilon. These are the various properties we have looked at. Let's now extend this, and what we want to do today is see what happens when we go through different mediums. Let's start with the simplest case, and this is the lossless dielectric. Lossless dielectric is you have mu and you have epsilon, and mu and epsilon are purely real. These are real numbers. There's no imaginary part to them. So mu is mu naught by mu r. Epsilon is epsilon naught epsilon r. For most mediums, mu r is approximately 1. So practically speaking, mu r is nearly 1 for most of the dielectric materials. If we now consider the various, if I consider phase velocity without square root of mu epsilon, so that becomes square root of mu naught epsilon naught, square root of mu r epsilon r. But then we had seen yesterday is nothing but the speed of light. So the phase velocity becomes square root of divided by square root of mu r epsilon r. This, how much does phase velocity decrease in a medium is what we call the refractive index. So if I look at the refractive index n, n is now square root of mu r epsilon r, and for most dielectrics, where mu r is approximately 1, the refractive index is square root root of epsilon r. This epsilon r is your epsilon r, mu r are your fundamental properties. We had basically defined these properties based on how electric fields and magnetic fields are enhanced or decreased within a medium. Epsilon r means that if I have a medium, when I apply electric field within that medium, I create a polarization. And that polarization now increases, the polarization is against the electric field. It creates an electric field which opposes my external electric field, and the total electric field value goes down. The refractive index is basically a term which we define out of these materials. And it turns out that the role of solid phase to be square root of ur epsilon r. If now I consider the value of k we have said was omega square root of mu epsilon, which is omega by Vp. And if you call this now, this becomes, if I substitute the value before, it becomes omega by C times N. Omega is 2 pi F by Cn. And yesterday we had defined the term, this term here, as free space wavelength. Lambda naught, and then free space wavelength was C by F. So my k now becomes pi by lambda naught into n, and this term over here is what we had called yesterday the free space wave number. So my k becomes k naught by n. And if I look at my wavelength inside, my wavelength inside the medium becomes lambda naught by n. Let's consider this. Let's say I have a medium here. Let's say here. If I have a wave coming in with a specific lambda naught, when it goes to medium one with refractive index n given by square root of mu r epsilon r, this wavelength inside the medium is going to get compressed. This is going to become smaller than outside, and how much is going to become smaller by? The same ratio with which the velocity goes reduces inside. The velocity of the wave outside is c. The velocity of the wave inside is c by n. The ratio with which the velocity decreases is the same ratio with which the wavelength will get compressed within that medium. Let me show you a quick demo why this is happening to try to help you understand this better. Let's assume, so think of me again as a wave, which we have talked about before. So think of me again as a wave. When I am talking is the frequency with which the time is changing. And basically, I have an electric field and a magnetic field with respect to that, and these are oscillating. And basically, what that is, as we had said yesterday, that I have to create a wave, I have to jump forward. Now, jumping up and down, that will be the time variation which I have. That time variation does not change. So if I am in a medium, if I am in air, I have larger velocity, but by jumping up and down takes the same amount of time, I would make longer hops. I would be able to travel further apart, further down by the time I come down. On the other hand, if I go where my forward velocity is decreased, and I'm jumping up and down but at the same frequency, that time I take to jump up and down is the same, but now I cannot move further, further, then my hops will have to decrease. But this hops forward will have to decrease. So the wavelength in a medium, wavelength inside the medium gets compressed based on the refractive index I have. What would the wavelength be? The wave is still looking slightly Z. This point, eclectic field is pointing in its direction. I have AE minus JKZ, but that is just a phasor form. That is a form which we had defined it to be in one. We had only taken the space part of it. The wave in reality is ZT. Remember, we had EJ omega T. This would be A E minus JKZ EJ omega T. If I take the real part of this wave, which is a real function which I'm working with, this becomes A, assuming A is purely real, becomes cos of omega T minus Kz. And with respect to that, I would also have an H which is in y direction, which would be A cos of omega T minus Kz divided by my value of eta. What happens to this eta? Eta Z was square root of mu by epsilon, and it's square root of mu naught mu r epsilon naught epsilon r. This first term is what we had just called eta naught yesterday. This becomes eta naught square root of mu r epsilon r. For most dielectrics are not magnetic mediums, are not ferromagnets. Mu r is approximately 1. So my eta becomes eta naught square root of epsilon r, and then would be the refractive. So this becomes eta naught divided by n. So my wave impedance in dielectric also decreases by the refractive index. Remember, from here, wave impedance is maximum for free This will become important when we start to design structures later on, when we do unit 5 and some interesting designs like anti-reflection coatings, designs like high-reflection coatings we can do. Using this wave impedance there, and this concept would become very important at that stage. Wave impedance is going to be maximum for free space. In dielectric, this impedance is going to decrease by refractive index ratio. All right, this is what is happening for dielectrics, which are no loss. Let's go to the second case, which is lossy dielectrics. Lossy dielectric, we have said that absolute is not real, but also has an imaginary part, and mu can also have an imaginary part. So absolute is not just purely real, but there is an imaginary component to it too. Let's figure out what this imaginary component is going to do to you. If I consider my refractive index n, that is square root of mu r epsilon r. If I look at this refractive index, this is epsilon r and mu r, I get epsilon prime minus j epsilon double prime, mu prime minus j mu double prime in general case. And if you now notice, this will have a real part and an imaginary part. This square root of this complex function, square root of any complex function is going to have a real part to it and an imaginary part to it. So n is normally written as n minus jk. There is a real part, so there is an imaginary part to it. This k has nothing to do with big numbers. Good place for you to go would be to refractiveindex.info website. And you can see the refractive index of various materials at various frequencies around the world in different materials. And you'll see that you will have a real part there called n and an imaginary part there called k. But n and k do not, the k part is not, has nothing to do with the refractive index term. Nothing to do with the wave number. So for this course, so that we don't have that confusion, let's just call n to be n real minus j n imaginary to understand what is happening. So n imaginary is going to be k, n real is going to be n in the databases. If I consider my wave, my solution still does not change. My wave is of the form of Exz, A E minus jk z, pointing in x direction, propagating in z direction, but the field is pointing in x direction. K we had said was k naught by the refractive index n. K naught multiplied by the refractive index n. K we had said was omega, square root of mu epsilon, omega by Vp, omega by C into n, and omega by C is k naught. Free space wavelength, 2 pi by the naught. So for these lossy dielectrics, K now becomes k naught n real minus j n imaginary. And if I look at my wave, this becomes a e minus j, substitute the value of k in it as k naught n real minus j n imaginary z, pointing in x direction. So this becomes a E minus J K dot and RZ. And when I do the second multiplication, it becomes J minus J multiplied by minus J. So that's J square, which is minus 1. So I get a term which is E minus K dot and I Z in X direction. If you look at this part here, this part is still the propagating part. This is your wave. But now it looks like that the wave has been modulated, that wave has another term in front of it, and that term is saying that the amplitude of the wave is going to decay. If you note this function here, this is a function with as z increases, this function is going downwards. This is an exponentially decaying function, e minus k naught n I z. This function is telling you the attenuation of the wave. So when I look at this complex function now, I have a part, this one over here, I have a part here which behaves like a wave, e minus jk z is behaving like a wave, but it's saying that as the wave is traveling forward in z, its amplitude is somehow decaying by that term. To understand this, let's see what E Z E would look like. That would be, let's just say I want to look for the cost solution. It would be real of A E minus J K naught N R Z E minus K naught N I Z or pointing in X direction multiplied by E J omega T. That becomes real of A E minus J K naught and real Z. So let me put minus inside. Plus omega T. That part is your wave part. And then you have E minus K naught and I Z pointing in X direction. Or it looks like A E minus K naught and I Z. And if I take the real part, only this part has the real and the imaginary part. So this becomes cos of omega T minus K naught and real Z. That is what the electric field now starts to look like. What does this mean? This means that I have a function here which is multiplied by another function. So I have one function which is behaving like that as z is changing. It starts off at z is equal to 0, it starts off at 8, and then it decays by a certain constant multiplied by a function which is the cost function around that. Anytime you multiply two functions like this, and in next year when you start doing communication courses, you will do a lot of those multiplications. Anytime when you have to multiply two functions like this and you want to visualize what those functions look like, what you do is you have a cost term here which is changing from +1 to -1. And you have a function which is varying slowly with z. There is one function which is varying fast with z, the periodic fashion, and another function which is varying slowly in z. Anytime you have to do this multiplication and visualize, what you do is take this slowly varying function and you create an envelope. So you take that slowly varying function with z and you create an envelope over here. So you say this is a e minus jkz, and you go below and you do minus a e minus jkz. Remember, if I take a look at this, when I multiply here by this, I get plus a, but when I multiply a point here, I would actually get a minus. So you create an envelope of the function, which is slowly varying. How you create the envelope is you take the function and you mirror image it on your axis. So you go to the negative side and you mirror image it, and your multiplication function is now going to be bounded by that envelope. As this function is going forward, this function is now going to be your a e minus jkz, not k but n r, k naught n r, k naught n r z cos of omega t minus k naught n I n n r z. As time progresses, this part is still a wave. This part over here is still a wave. As time progresses, this part is moving forward. This part doesn't change. As time progresses, this wave has moved forward. If I go to a different time, this wave would have moved forward. So with different times, this wave is moving forward. What you now notice is, as this wave is moving forward, the peak values are decreasing. As the wave is moving forward, the peak values are decreasing, which tells you wave is losing energy. Wave is losing energy as it goes in Z. As the wave is moving forward in Z, the wave starts to lose its energy. So now if you look at the terms we have n we said was n real minus j n imaginary. And we said that the wave part now looks like a e minus j k n real z, e minus k n imaginary z. This part, this n real part, tells you about the propagation. And speed of wave. The phase velocity would be given by, now omega would be given by c by n real. If you look at k, so this was k naught. If you look at k, my k naught is k naught, k in the wave is k naught by n real. This becomes 2 pi by lambda naught n real. So my lambda within that material has gone to lambda naught by n real, the real part. So the real part tells you about the propagation and speed of the wave, and this is your propagation term. And the imaginary part, Ni, tells you about the loss. And the word we normally use is attenuation. It tells you about how the power is being lost as the wave is traveling forward. We define a constant called attenuation constant, alpha, so that in RF field, alpha is described on electric field. So if you consider the wave which I have, E, xz is AE minus J K naught N real Z, E minus K naught N imaginary Z. This term here is called alpha. So alpha is K naught N imaginary. K naught we had said was 2 pi by lambda naught, free space wavelength, and imaginary. There's also a term called loss tangent. And this is typically only used in RF field. And loss tangent is defined as some angle tan theta, which is given by epsilon double prime divided by epsilon. It's a measure of loss in the medium. The larger the value of tan theta, the stronger, the larger the loss would be. The larger epsilon double prime is, the larger your N imaginary would be, the larger your loss is. On the other hand, in photonic field, if you go to photonics, if you are going to go and look at, for example, fiber network or semiconductor lasers, in photonics, alpha is defined on power or energy. And alpha, I'll later on talk about Poynting vector, so this will become clear why. But alpha in photonics is going to be 4 pi by lambda naught and imaginary. It will be twice that of alpha of RF field. So just to recap, just to review, in a lossy dielectric, we have the wave which is going to be in Z direction pointing in X is going to have the propagating term E minus J K naught N real Z E minus alpha Z pointing in X direction as we have done it. This term here, K naught by NR, is also called propagation constant beta. So beta is 2 pi by lambda, the wavelength, which is 2 pi by lambda naught N real. If an imaginary is 0, if it is lossless, then beta and K are exactly the same thing. But now I'm saying that K forms, if I now take a look at this term here, if I take a look at this equation, E x z is A E minus J beta Z, E minus alpha Z, pointing in x direction. I can write this as A E minus J beta minus J alpha Z in x direction. For lossy dielectric, your K is beta minus J alpha. That's your total K value. Many times when you look at the books, and I believe your book also does it, this is also called gamma. They go through some complex math, but the math is very, very simple. They just, many of the RF books, books written by RF people become too confusing in maths. And they normally call this to be gamma, and then they will tell you that the solution is e to the power of minus gamma z, which is basically fundamentally the term over here which we have. Beta now represents your propagation. Alpha represents your loss. Everything else is the same. Let's take a look at eta too. Eta is mu by epsilon. You can write this as mu naught mu r, epsilon naught epsilon r. This part here is nothing but eta naught. Mu r, we said, has real part and an imaginary part in general. And this has a real part and an imaginary part in general. So your eta is complex too. What is eta? Eta is how F is related to E. It's telling you that eta has some real part to it plus some imaginary part to it. When I solve this over here, I'll get some real part and I'll get some imaginary part. So eta would have some real part and some imaginary part. What this basically means is that H and E are not in phase anymore. When E is maximum, H will not be maximum. This is the illustration I did yesterday. Where my two hands are not in sync with each other. My one hand is going at my one hand is going, when my one hand is maximum, my other hand is probably somewhere still in the middle. So E and H are not in sync with each other. They are not in phase with each other. But both E and H have to still exist. All right, that is for lossy dielectric. Let's extend this further to conductors. As you may have in your unit 3, you would have seen that conductors have a conductivity given by sigma. And your Ohm's law was J is sigma E. To get to Helmholtz equation, which is what the solution we are looking for. We are looking for the solution of the Helmholtz equation. To get to Helmholtz equation, we had put J to be 0. Remember that? Like we had said that there is no source to the obedience. We had put J to be 0. But in conductors, J will exist. As soon as I apply an electric field to the conductor, the electrons will start moving. Electrons are free to move in a conductor, so the electrons will start moving and thus will start creating a current within the conductor. So it's not apparent that I can use my previous analysis to get to conductors very easily. Let's go back to Ampere's law. And Ampere's law has said del cross S is J plus del D by del T. And let's substitute Ohm's law in there. And we get del cross H is sigma E plus epsilon del E by del T. If I put E, X, Y, Z, E is E, X, Y, Z, E, J, omega T. If I put that, I can write this equation now as del cross S is equal to sigma E, only in space now, plus J omega epsilon E. Let me take J omega epsilon out of the equation. I get J omega epsilon. I get 1 plus sigma by J omega epsilon E. One thing you notice very quickly here is if I call this to be a single term, let's call it epsilon of for a conductor, this equation boils down to J omega epsilon conductor E del cross H. And remember, for source medium, the analysis we had done was del cross H is J omega epsilon E. This is the equation we had used to get to Helmholtz equation. Now if you look at it, as a conductor to be within this, to be whatever is this term over here, as soon as I do that, my equation just boils down to be very similar to what I had done previously. So all I have to do for conductors is replace epsilon with epsilon C. In all the analysis I've done before, the epsilon C is epsilon 1 plus sigma J omega epsilon. If I take this term, if I take a look at this term here, this becomes epsilon 1 minus J. If I take 1 by J up, 1 by J sigma omega epsilon. And you notice this is turning out to be again of the same form, epsilon prime minus j epsilon double prime. So in a conductor, I will have loss and a propagating term. Why do I have loss? I have the imaginary part of epsilon present, and then there will be some propagation to it too. Now for most conductors, and that's where we really call them conductors, your sigma is much, much larger than omega epsilon. Your conductivity for most conductors is much, much larger than the term below. So I can basically say that sigma by omega epsilon is going to be much, much larger than 1. So only this term is of importance. So my epsilon conductor, I can approximate it as minus j sigma by omega. Good. Let's assume mu r for the conductor is 1. And just going back to what we had discussed before, my K is omega square root of mu epsilon. If I substitute now for conductors, I have to just substitute this to be omega t. So this becomes omega square root of mu epsilon 1 minus j sigma by omega epsilon, the square root of that. And if I assume that this condition is true, then my K becomes omega square root of mu epsilon sigma minus j sigma by omega epsilon, the square root of that. If I take this K, my K now becomes omega and square root of omega. 1 will go away. So this would be 1 by square root of omega. Square root of mu. Square root of mu sigma and square root of minus j. Sorry, I made a mistake. This would be omega on the top. So my K becomes square root of omega mu sigma square root of minus j. Let's figure out how I can do this minus square root of minus j. Again, we are ingenious, so let's use phasors. I can write this as minus j is minus j pi by 2. So that just becomes square root of e minus j pi by that just becomes e minus j pi by 4. So that becomes cos pi by 4 minus j sine pi by 4. Or it becomes 1 minus j square root of 2. So k here is now square root of omega mu sigma 1 minus j square root of 2. I can write this as omega mu sigma by 2 minus j omega mu sigma by 2. This becomes my beta minus j alpha. So for conductors, for good conductors, my beta is going to be equal to alpha is going to be given by omega mu sigma by 2. If I have this wave is traveling by E minus alpha z, which means that I get to z is equal to 1 by alpha, and z is equal to 1 by alpha. If I take the wave would have this at z is equal to 0. My wave was a e minus j k z, e minus alpha z. I put z is equal to 0, my wave is equal to c. At z is equal to 1 by alpha, my intensity of the wave drops down to a e minus alpha 1 by alpha, or is a e minus 1, or a by e, which is approximately 0.367. The intensity, the electric field value of the wave by that time drops, decreases within the conductor very quickly. So if I have Z in the conductor, I start from A, as I go further down, this intensity drops. When I go to a distance 1 by alpha, the intensity has dropped down to about 0.367 of A, which I started with. This length Z is equal to 1 by alpha is called the skin depth. It's a measure of how far the wave will penetrate in a conductor. And you would notice few things. Your alpha depends upon your conductivity. Larger the conductivity, larger the alpha. The alpha also depends upon the frequency. The larger the frequency you apply, the less the wave would travel inside the conductor. If I take your transmission line, which is a wave at 60 Hz, it would be probably be able to penetrate deeper into the conductor, whereas if I go into RF, the penetration depth as omega goes close to a few gigahertz, this penetration depth may be only a few microns. And this depth is called the skin depth. One last concept in conductor is what happens to eta. Eta, we had said, was square root of mu epsilon. So because I'm in a conductor, I'm going to call it square root of mu epsilon c. And we had said epsilon c for a good conductor was approximately sigma by j omega epsilon. So sigma by j omega sigma by j omega was your absolute C. So if I substitute it here, I get square root of mu by sigma by j omega. So I get a square root of j omega mu by sigma. Square root of j, I can write it as e j pi by 2. That is j. Omega mu by sigma. So that becomes e j pi by 4. Omega mu by sigma. Or it becomes 1 plus j square root of 2. Omega mu by sigma if you want to calculate the value. But let's consider this term over here. My h is e by eta. So h now becomes e divided by e j pi by 4 square root of omega mu by sigma. So h is e minus j pi by 4 e square root of omega mu square root of sigma. Two things you notice from here. One, because of this large number, sigma is a large number in conductor, h is going to be larger than e. Because of this sigma being a number which is in 10,000 to 100,000 range, this term here, because of this term, h is going to be a dominant term inside the conductors. And that's not surprising, because inside the conductors I have the current and the current sources create h. And the other thing you notice here is this part here. H lags behind E. By pi by 4. When E is at 90 degrees, when E is at maximum, let's say I'm using the sine form, sine 90 is maximum. When E is at its maximum, H is only at 45 degrees. H is only 1 by square root of 2 at that point. When E to maximum is decreasing, H is still increasing towards its maximum value. So the two hands which I have, they are not in sync with each other. When my left hand, when my right hand, which was E, which was horizontal, is at its maximum, my left hand is only at the middle point. And as this right hand of E is coming in, my H hand is still going up. So E and H inside the conductor are not going to be in sync with each other. Alright, Jay, how much time do you have, or they probably have to go for another class, I guess, now?
Sir?
Do we have time?
I can't get you.
Sorry, what is it? I didn't understand.
Yes, sir, we have.
Do we have time?
Now, sir, yes, you can proceed for 5 to 10 minutes, sir.
We can proceed, or this would be a good point to stop actually. Otherwise, we have to start a new topic. Okay, let me do the pointing vector quickly.
If you want, you can take for 5 to 10 minutes, sir. 5 more minutes.
5 more minutes, okay. Let me finish the pointing vector then. All right, let's consider. So, look at E and H fields for the waves. We also need to understand how is the power or intensity propagating in a wave. The term we call pointing vector. I won't go through the derivations of these. Let's just understand what this vector means. It's a vector given by S. The vector S and is given as E cross H. The direction of S
This is also important topic. Listen.
gives the direction of wave, gives the propagation direction. The magnitude of S gives the intensity distribution in XY plane. Again, remember, E is propagating in Z, but it has amplitude variation. It could have amplitude variations in XY plane too if the wave is constructed in that direction. So the direction of S gives the propagation direction. If you notice, what would the direction of S be? The direction of S is E cross the direction of H. We have already seen that this product, this cross product, tells you the direction in which the wave is propagating. The magnitude of S is how the intensity, how the power in the wave is distributed in the XY plane. If I was going to calculate the total power, that would be integral of S in dx dy plane. Let's consider this vector E cross H for plane wave. The wave we have already considered. We know your E is A E minus j k z, but also E j omega t in x direction. This is cross product with your h value, which is A E minus j k z. That term doesn't change. E j omega t doesn't change, divided by eta in y value. So if you now know this would be A E minus j k z E j omega t square divided by eta x cross y, and this we have said is now A E minus j k z E j omega t square eta in z direction. This is propagation direction. This part here is your instantaneous intensity in the wave. At any one specific time, what would the instantaneous intensity be? Normally, we are never interested in instantaneous intensity. We are interested in average power or average intensity over a time cycle. Normally, this is what we are interested in. We also have an average pointing vector. And without going into the math, just connecting it with what you have seen before, from circuits, you know, If I have Vp and It as some sinusoidal signals, my instantaneous power at any time is Vt It. My average power is half Vi star. If I'm using sinusoids and if I'm using phases, this is what your average power is from circuits. So it's telling me the average wave intensity S average Z. It's still going to be a vector. It is going to be half of, sorry, this was real. Half of real. V we said was electric field, equivalent to electric field. I we said was equivalent to H. And you have a cross product with a wave. This gives you the average intensity over a time cycle carried by the wave. And this E and H are the space variance only. We have removed the time component out of here. This is how they are changing in space. Let's quickly do one more equation. Our S average Z, this is half of real of E cross H star, but H star magnitude we know is magnitude of E by eta. So I have half of real of E by eta star, this being the complex conjugate. E, if E is in X direction, this would be in Y direction. So it becomes half of real of E X cross E by eta complex conjugate in Y. I can write this as half of real of E star becomes magnitude of E square. This is eta star. X cross Y is your Z. Magnitude of E square is always going to be real. So this becomes half E square real of 1 by eta star in Z direction. And with that, you can calculate your average intensity within a wave. All right, let's stop here. What we'll do next is extend this further by adding polarization. So far, we have only said that the electric field is pointing linearly. Tomorrow, we'll see, can we do other funny stuff with the electric field directions and whether that leads us to something new. Yeah, up to you. All right. Jay, normally I turn the go-to meeting around half an hour before the class. So if you are not able to connect, let me know immediately. I'll send you my Skype number too, so let me just know you immediately if you're not able to connect. Otherwise, I see you tomorrow.